this computer, yeah, record and share screen. Screen is being shared. Screen is being shared now. Okay, good. So now let's start today's lecture. Okay, and in the previous lecture, we actually stopped right here. We actually go through the breadth search algorithm, the dry run of the breadth search algorithm in a very brief manner. Okay, so we'll just a brief recap. We'll talk about breadth search algorithm as we already go through this already in the previous lecture. If you take a look on the source code that is given in the Moodle, you will find that both the breadth search and the depth search, their structure is quite similar to each other. Okay, the major differences is that we are using the queue for the breadth search and we are using the stack for the depth search. Okay, and in fact, one thing that I need to remind every one of you is that depth search can actually be implemented in another manner. Okay, so just a brief recap, okay? Do you recall when you learn Python in year one? Have you learned a concept called recursion? Anyone? So so anyone can tell me what is the meaning of recursion? So what is the meaning of recursion? Anyone? So what is the meaning of recursion? Yeah. Essentially, recursion is calling the function itself. But this is actually not being discussed behind the hood. Okay, so essentially how functions is being managed when they are being called. You learn that a function is being called, okay, and the computer will execute it, okay, and this behavior will be managed by the computer. Okay, so you didn't think twice when you are calling a function. But in fact, you can actually look up in the internet something called a call stack. Something called a call stack. So essentially behind the hood, behind the scene, okay, the computer would actually manage the function that you call in a hidden data structure within the operating system called the call stack. Okay. So essentially, the computer actually manage the function call with a stack. Okay, so that is the reason why. Essentially, when you are writing function using the recursion technique, you are actually using the built-in stack to manage your function call. Okay. So this is the first thing you may want to know. Okay, when you are working with recursion, the moment you write recursion function, you are actually using the built-in stack of your computer to manage your computing operation ordering. Okay. And we also talk about one thing. Depth search is based on stack. Okay. Depth search is based on stack. And when we are writing recursion, we are actually using the call stack to manage our function call ordering. So is there a chances that we can write depth search using recursion? And the answer is yes. We can actually write depth search using recursion. Okay, and I will have a dedicated slide to actually talk about the background of this approach. Okay, but I would need to talk about it beforehand. And the reason why is that I understand that many students here are active learners. Okay, they may try to investigate. Okay, so-called breadth search and depth search using ChatGPT or other large language models. If you use large language models and you ask the large language models to generate source code for depth search, or if you find reference materials about depth search on the internet, most likely you will see this one. Most likely you will see the depth search is implemented in a recursive manner. Okay? And the reason why is that depth search is based on stack. Instead of manually explicitly implement a stack, a more easy approach is that we just use recursion and use the last in first out properties of the function call that is provided by the call stack to make sure our node exploration is done a last in first out order. Okay, instead of explicitly using a fringe, we can actually use the recursion and use function calls and use the ordering of the function calls to control the ordering of the node exploration. Okay, so that is the reason why when you use ChatGPT or if you use other large language models or if you are finding reference materials about depth search on the internet, you often find this one, the recursive version, and that's the reason why. Because this one is more easy to implement. And if you are more used to the recursion programming paradigm, you will find that the recursive version of the depth search is more easy to understand. Okay, but because we are introducing the depth search gradually, okay, from scratch, okay, so that is why I also included the depth search with the implementation of an explicit stack, and that's the reason why. Okay. So any questions? So now let's get back to the breadth search. Okay. The reason why I need to explain this beforehand is that I understand that many students will make use of ChatGPT or other large language models to assist with your studies. And if I do not explain this beforehand, you will feel extremely confused why depth search is implemented differently from the reference material you can find on the internet or you can find in reference books. Okay, so any questions? Any questions? And in fact, if I do not explain this, you may feel confusing. Why in the source code I included two different implementation of the depth search? Okay, and the reason is the ones I just talked about. So now let's go over the depth search. Okay, breadth search. Okay, in a breadth search, essentially, this slide is actually showing the dry run. Is showing the dry run process of the breadth search. Okay, and in this slide at the left hand side, you can see that the area is dedicated for showing the search tree. At the right hand side, at the upper corner, we have the search space. And at the bottom corner, we have the queue that is the fringe. Okay, and one thing I hope everyone here will understand is that the search tree we included in this slide is just helping with our conceptual understanding. Okay, if you really go into the implementation, you will actually see the breadth the search tree is actually just the search node connected to each other. Okay, this is something that I hope everyone could understand. Similar to to the things you learn in data mining, right? In data mining, when we are talking about the linked list or the queue or the stack, we draw them out as squares connected to each other with arrows, okay? But in reality, computer doesn't actually store that image, okay? Doesn't actually have that data structure as an image form, okay? Essentially, within the computer memory, all these data structure are just objects connected to each other by object reference. Okay, this is something you should understand. Okay, the search tree I draw here is just for the sake of discussion in a written manner. Okay, but you need to know behind the hood when you really implement it into the computer, the search tree doesn't really is a image like this. Okay, it is essentially just some objects connected to each other with object reference. Okay, so now we are in this example, we have a reduced state diagram. The reason why is that the server space diagram is so big that it is not good, it is not easy for the sake of demonstration. Okay, so I reduce the size of the server space to be smaller. Okay. And one thing I may not be able to discuss it in a previous lecture is that there are some notation information that you should know about network or graph in data science or computer science. Okay, so when you are reading reference books, okay, when you are reading reference books, when you are reading reference books, okay, about networks, okay, in the future, or in your own interest, okay, when you see network that have edges, doesn't have any arrows, okay, as you can see in this diagram, okay, the network here are having nodes connected together by edges, okay, and these edges doesn't have arrowhead. Okay, you can see all the lines here doesn't have an arrowhead. Okay, if I see edges doesn't have arrowhead, it often means that this network is having bi-directional connections, meaning that the connection is both ways. Okay, for example, the array is connected to series in a line that doesn't have arrows. That means that the agent can move from series to array or from array to series. Okay. Okay, this is something you must know. For example, for Cebu and Fagorous, these two states is connected to each other with a edge without arrows. That means that the direction of the action is both ways. You can go from Cebu to Fagorous or from Fagorous to Cebu. Okay. In computer science and data science, when you say network that the edges doesn't have arrowhead, it actually means bidirectional. The direction is both ways. Okay, okay. The connection direction is in both ways. Okay, okay. And the reason why in this diagram we do not include any arrowhead is that in many situations, in most situations, okay, when you have a row network, the connection should be both ways. Okay, since the connection of the row network is in both ways, then the state diagram should also have without any direction, or I would say is should be bidirectional for all the edges in the network. Okay, so that is why we don't include any arrowheads. Okay, but in this diagram, okay, in the Webkin world kinning state diagram, okay, the edges here are referring to the transition from one state to another, and in this Webkin kinning graph, okay, the transition is one way, but not both ways. Okay. For example, if you set the dust in this state, okay, then the dust will be removed and it will get to this state. Okay. You cannot create dust in thin air and get back to this state. Okay. You can, if your state reaches this, if your agent reaches to this state, you cannot create dust out of thin air and get back to this state. Okay, notice my cursor. Okay, so if the agent is in state, then the agent already cleaned both rooms. Okay, and it is not possible for the agent to arbitrarily create some dust and let the swell core return to the state with the dust. Okay, so that is the reason why in this state space diagram, all the edges here contains arrows, and the arrow is indicating the direction for transition. Okay. So any questions? So any questions? So this is something you should be remember. Okay. Not just for this course. Okay. In the future, you may be studying courses about network analysis, for example, social network analysis, and you may come back to the topic of connectivity of networks again. Okay, so a common convention is that an edges with arrows that the arrowhead will be representing a direction of transitions. If the edges don't have any arrows, then you may assume that the direction of the transition is both ways. Okay. And as you can see here, you may find that the examples I listed right here also contain arrows. Okay. And the reason why is that I want to reduce the complexity of, I want to make this diagram more simple. Okay. In order to make this diagram more simple, I actually make the transition between cities from both ways to one way. Okay, so that is more easy to do discussion on. Okay. Okay. But in fact, both if it's both ways, you can still use the algorithm to handle it. Okay. And also in this diagram, you will actually notice that we have numbers right next to each edge. Okay, the number right to each edge is representing the step cost of that transition. Okay, so for example, if consider edge from mutual VCHA to p-test. Okay, the arrow here is pointing from mutual VCHA to p-test. That means that the agent can transit from mutual VCHA to p-test, but the other way around doesn't work. Okay, the agent cannot transit from p-test back to mutual VCHA. Okay, and the 90 and 97 next to this edge means that the agent needs to take a course of 97 to transit from mutual VCHA to p-test. Okay. And the Q head here is actually showing the status of the fringe. Okay. Essentially, when we are working with depth search, okay, we need to use the fringe to keep a record on the unexplored node up to now. Okay, so as a result, we also include a section in this slides to visualize the content in the fringe. And initially, just before we conduct the search, okay, in this simplified state space diagram, we want to find a sequence of action that allow us to transit from Cebu to Bucharest. Okay, from Cebu to Bucharest. Okay, because we are trying to find a path from Cebu to Bucharest. Okay, so the first initial state is the Cebu. Okay, so in the right in the left hand side, the search tree is having the Cebu as the root node. And if you take a look on the fringe, okay, the fringe is also having the Cebu as the first element being pushed into the Q hat. Okay. Okay. And then we have Cebu here. And because the Cebu is the only node here, the Cebu is the only node in the Q hat available for exploration to be extracted from the fringe for exploration. So the Cebu is actually being removed, and we are now taking the Cebu for exploration. And when we take a look on the network at the right-hand corner, at the top right-hand corner here, we can see that the Cebu have two arrows pointing to Pythagoras and Remedial V-char. So the Pythagoras and the Remedial V-char are actually the two states, the two neighboring states that the agent can go to from CBOR. Okay, so as a result, the Pythagoras and Remedial V-char is added to the queue. And we also see the Pythagoras and the Remedial V-char being added to the search tree as well. And you may also notice that in the French, okay, the CBOR is being dequeued, is being removed, okay, because now the CBOR have already explored by our algorithm. So CBOR should never be still in the fridge. Otherwise, the algorithm will be wrong, okay? So as a result, we want to keep all the nodes in the fridge as unexplored node. So as long as a node is being explored, we remove it. Okay? Okay. And then we explore Pythagoras. Okay. Okay. You may ask is that Professor, so why have Pythagoras and I have Remedial V-char here? So which I should explore first. Okay. In fact, this node have the same depth, okay? So it doesn't matter which node you explore first. Okay? You can explore Pythagoras first, or you can explore Remedial V-char first, okay? Both are correct. Okay? Okay. But of course, okay, you can also impose additional constraint. For example, you may want to explore the nodes that have a smaller alphabetical ordering instead of a node with a high alphabetical order, for example. Okay, but in the context of the backward search, it doesn't matter. Okay, it doesn't matter you explore the Pythagoras first or explore Remedial V-char first. Okay, both are still correct in this context. Okay, and then we explore Pythagoras first, and if we take a look on the node Pythagoras, okay, we can actually see there is a edge pointing to Bucharest. Okay, there is a edge pointing to Bucharest. Okay, and because Pythagoras only have one neighbor, so the moment we explore Pythagoras, we remove it from the queue, and we also include its only member Bucharest into the queue. Okay, and we also add the Bucharest into the search tree. Okay, into the search tree. Okay, so that is what you see here. Okay, and the next question is we explore Remedial V-char first or we explore Bucharest first. Okay, because we are using a queue for our fringe, so the Remedial V-char being added to the fringe earlier because it is being seen earlier. Okay, will get explore first. Okay, okay, so the reason why we choose the fringe, okay, the reason why we choose the fringe, we choose the queue as the fringe for backward search is that backward search try to prioritize nodes that have a shadow, that have a smaller depth. Okay, the backward search is prioritizing nodes that have a smaller depth. Okay, a node that have a smaller depth in the search tree would also mean that this node is appear earlier in the search tree. Okay, the reason why is that the search tree is actually grow from the top to the bottom. Okay, each time when we are adding node to the search tree, we are not adding the node at the bottom, at the leaf of the search tree. Okay. Okay, each time we are adding new node to the search tree, we are adding those nodes at the leaf node of the search tree. So the leaf node, okay, so the node having a high depth will appear later than the node that have a smaller depth. Okay, the node that have a smaller depth and closer to the wood is appearing earlier than the node that have a higher depth. Okay. Okay, we grow the search tree from the top to the bottom. When we add node to the search tree, we add node to the bottom of the search tree or the leaf node of the search tree. Okay, so in the search tree, okay, the depth of the search tree is strongly positively related to the timing of the node being inserted in the search tree. A node that has a smaller depth means that it is added to the search tree earlier. Okay, so we can actually use the timing or the ordering of the node being inserted in the search tree as the criteria to represent their depth. So as you can see here, this is the reason why we use the queue to control which node should explore first. Okay, to understand why the queue can be used to control the shadow node being explored first, you need to remember one core issue, one core properties of the depth or of the search tree. A node that has a smaller depth will appear earlier in the search. Okay, because of the construction, because of how the search tree is being constructed during the search, okay, all the new node were added at the bottom of the search tree, okay. So if you scan the search tree from the root node to the bottom, you will find that as the depth increase, their time, okay, that is included in the search tree is also increased, okay, meaning that the node that is deeper, they are added to the search tree later. Okay, it makes sense, right? Up to now, all the things still make sense, right? Okay, so you need to remember these properties, okay? If you can understand and observe these properties, then you understand why we use the fringe, why we want to queue to feed the fringe, okay? We are making use of the properties that a shadow node will always appear earlier in the search, and these observations to support our use of the queue as the fringe. Okay. Okay. And as a result, the remedial feature is occurring earlier, is being appear earlier in the queue. So the remedial feature will get processed first. Okay. And when we see remedial feature appear earlier, then the appear in a upper position closer to the head, then the brokerage will also tell us that the remedial feature appear earlier than in the search than the brokerage. Okay. So we will explore remedial feature first. And when we are exploring remedial feature, they will also add pretesty and camera into the queue. Okay. And in this moment, okay, the Bucharest is closest to the head. So next time we'll explore the Bucharest. Okay. And because the Bucharest is our goal state, so in this state, we can stop our search. Okay, we can stop our search. Okay. So let's talk about complexities. Okay. So for the breadth-first search, okay, it will always be complete. Okay, it will always be complete. Okay. Is as long as the branching factor, okay, that is the number of neighbors, of the search tree, or number of neighbors of each node is finite, okay, then the breadth-first search is always complete. Okay, so let's consider the breadth-first search video we talked about. So if we visualize the breadth-first search, okay, you can see the breadth-first search is covering the whole search space as a wave. Okay, so no matter where your goal state is, okay, the breadth-first search can always able to find a solution, and that's the reason why. Okay. And for the time complexity and the space complexity, I would actually talk about it. I will actually talk about it with a PowerPoint. Okay, with an extra PowerPoint. Okay. So so as you can see here, so this is a slide. Okay. that discuss the time complexity of backward search. Okay. So in this slide, what you can see here is a search tree. Okay. When we want to measure the time complexity of the backward search, okay, we are trying to abstract the execution time of the backward search. So we are measuring how much node that is included in the search tree, and we are using that as the criteria to measure the number of operations that the backward search need to perform to get to the solution. Okay? Okay? And and we make some assumption first, okay? We create some variable first, okay? When we want to work with abstraction, we need to create some symbols, okay? First we create branching factor, okay? The concept of branching factor is essentially defining how much children node a node can have. Okay? Okay. And I believe that you should learn about complexity is trying to measure the worst case scenarios, right? Okay. In most situations, when we are talking about complexity, we are measuring the worst case scenario performance. Okay. You learn about that, right? You learn about that, right? When you measure complexity of an algorithm, you are measuring the worst case scenario of that algorithm, right? You learn that, right? You have learned that, right? Okay, you actually know this, right? Any response? So maybe I'll ask, do you still remember do you still remember about the complexity you learned in data structure course? Anyone? Okay. So anyway, I will explain what is complexity first, okay? So let's talk about complexity. When you are measuring the performance of an algorithm, how we will do? What kinds of things we will do to measure the complexity or how to compare the performance of an algorithm? The most intuitive measurement you will make is the execution time and the memory that is taken to run the algorithm. Okay. For example, I believe that most of you here use your cell phone. So let's think about this, okay? If you want to play mobile games, okay? I believe that most of you here, your generation, okay? I'm too old for this, okay? But yeah, I believe that most of you here are playing some sort of mobile games, 3A grade mobile games in your mobile phone, right? Some sort like Genshin Impact or those kind of games, okay? So when you're thinking about playing a mobile games like Genshin Impact, okay? So when you are wanting to play the game, okay, you will always want to get the game loaded as soon as possible. Okay. So when you click on the icon and then you think Genshin Impact launch, okay, and then when the Genshin Impact is being launched, okay, if you will of course want the app to open to get launched and ready to play as soon as possible. You want the game to need several minutes to load before you can play. Okay, so that is the reason why when you are measuring the performance of an algorithm, you will want to consider the time. Okay, you will always want to get a job done more quickly. Okay. Okay. You will want to wait for a task to for a very long time in order to get a job being finished. Okay, so that is why measuring the execution time is important. And the second thing that we want to measure is the amount of RAM being used. Okay, so I don't know if you have this experience. when you are playing with your mobile phone, okay, suddenly I'm originally chatting with my friends through QQ or through WeChat or WhatsApp or whatever, okay? Or I'm opening up Facebook and or I'm opening up TikTok, okay, and I'm watching videos, okay? And after watching the videos, now I want to play games, okay? So I put all the games, okay, into the background and then I launch Genshin Impact, okay? So after I'm done with my game section of Genshin Impact, okay, and then I switch back to the original app I'm opening, okay? And I discovered that all the apps I previously opened are now being closed. Okay, have you ever had this experience? And the reason why is that Genshin Impact is taking up too much memory in your mobile phone, and your mobile phone have no choice but to quit the game app you previously opened. Okay, so essentially the game occupies too much RAM in your mobile phone that your mobile phone doesn't have enough RAM to execute other applications. So as a result, those other applications are being quitted, such as to allocate enough RAM for you to launch the Genshin Impact in the first place. Okay, so imagine this. Okay, if the Genshin Impact is taking up less RAM, that means that you can keep other apps not being closed when you are playing the game. So you can have more seamless user experience, right? Okay, so when we are evaluating the performance of an algorithm or of an application, okay, we also want to consider how much RAM it takes. Or have you ever had this experience that when you are using Chrome, you open way many tabs, that it make your computer very slow. Okay, I don't know your habit of using the Chrome, but I believe that some students here, they have the habit of using the Chrome. Like I will open 100 tabs when I'm using the Chrome, okay, and after I close the Chrome and I reopen the Chrome, I will just let the Chrome open the previous 100 tab I just opened them previously. Okay, then when you open so many tabs in the Chrome, do you notice that your computer can get very slow? Have you ever had this experience? Do you have the experience of opening a lot of Chrome tabs? You know what is Chrome, right? So when you're using Chrome, have you ever tried to open like 100 tabs at once? Or have you ever had the experience that if you open too many tabs in Chrome, your computer will slow down? The reason why is that each tab in the Chrome is actually taking up some amount of the RAM in your computer. And if you open too much RAM, if you open too much tab, then your computer doesn't have enough RAM to open other applications. So that is why your computer gets slow. Okay, so that is the reason why when we are evaluating the performance of an algorithm, we also want to take a look on the memory. We always want the computer program to run fast but with a small amount of memory. Okay, that is the most ideal situation. Okay. Imagine a Chrome that can load the web page extremely fast and take up so little memory. You can open 1,000 tabs. Okay, then that will be the most ideal internet browsing applications. Okay. Then the next issue that we have about time and space is that how we measure execution time and how we measure RAM usage. I can always get a computer to run the program, then I can know how much RAM it takes and how much time it takes to finish the execution. But then the issue is the fairness of comparison. Okay, for example, I test my program, I test the program A with the state-of-the-art GPU server that I have in Nanyang University. But when I'm testing algorithm B, I am using a second-hand used computer that I can get from a thrift store, or I can get from some second-hand store, or I can get from Taobao, okay? Okay, or I can get from Xianyu, okay? Okay, so or I can get from core cell, okay? Of course, this comparison will not be fair, okay? The computing power of a Nanyang University state-of-the-art GPU server will always outperform your second-hand computer that you can buy in a thrift store or in core sale or like Taobao, okay? So we want to create a measurement, we want to create a technique that we can use to compare the performance of two algorithms in a fair manner. The idea that we have is abstraction. Okay, we abstract away the hardware. So when we are talking about whether a algorithm is fast or slow, we actually let can frame it in this angle. If a algorithm can finish a task with least amount of instruction to the CPU, then it should be the fastest. Okay? If a algorithm can need to store the least amount of data in the RAM, okay, least amount of data points into the RAM, then it should take up less space in the RAM. Okay, and we also know that we also know that the instruction that the algorithm need to take to finish a task should be strongly related to the amount of the data that is given in the first place. Okay, so let's consider this. Okay, I give you n tasks. Okay, if each task you need to do one operation, then you need to take n operation to finish that n data points. Okay, if I have n piece of data, and each data point I need to do one instruction to finish execution, then I will need to do n times. I will need to take n instructions to finish those tasks. Okay, or if I have n data points, okay, then I would properly need to store that n data points into my memory to process it. Okay, so in that sense, okay, we can actually express the number of instructions or the number of data points that need to be stored in the memory in terms of the number of data points. Okay, so when we are working with complexity, we are measuring how many instructions that we need to carry out given the amount of data point that we have. Okay, and for the space complexity, we are measuring how many memory space how many data points we need to store in the main memory to make this algorithm works. Okay. Okay. So up to now, any questions? Any questions? And when we are talking about the time complexity and the space complexity, we will actually need to talk about the search space, the search tree. Okay. So when we are running the search algorithm, the major operations are done with respect to the search tree. Okay, all the operations we done here are done with respect to the search tree. Okay, and if our queue is implemented in a good manner, okay, then the adding element and removing element and queuing or dequeuing a queue should take only O1 space complexity. Okay, it only takes around 1 to 2 instructions to get an item from the queue or add an item to the queue. Okay, I believe that you should at least learn this in database data structure talk. Okay, you know that when we are working with queue, when we want to add items to the queue or if we want to retrieve items from the queue, it only takes about 1 or 2 instructions. Okay. Okay. So the majority of the instruction we need to consider when we are executing the backward search is manipulating the nodes in the search tree. So you can consider the time complexity and the space complexity of the search algorithm roughly equal to how many nodes is being generated or being expanded for the time complexity. And for the space complexity, we are talking about how much number of nodes is stored in the main memory. Okay, then that will be our measurement for the time and the space complexity of the depth search and the breadth search and the other tree search algorithm as well. Okay, okay. So up to now, any questions? Any questions? So let's get to the time complexity discussion of the breadth search. Okay. So when we are talking about breadth search, we already talked about one issue. We are measuring the number of nodes that is expanded in the process, okay? And every node that is expanded in the process will get added to the search tree, okay? So by just counting how many nodes we have in the search tree, we know the time complexity of our breadth search, okay? So as you can see here in this slide, we have the breadth search, okay? And we make some assumptions and we introduce two symbols. The first symbol is called the branching factor. The branching factor is talking about how much children node you have for a node in the search tree. Okay, and we also introduce a symbol called a D. The D is talking about the depth of the optimal solution. Okay, and based on the properties of the breadth search, we know that the breadth search is scanning is expanding the node in the search tree in a layer by layer fashion. Okay, and we assume that the node is being expanded in one layer from the left to the right. Okay, we also take this assumption as well. Okay, and after taking this assumption, we know that the worst case scenario of conducting the search will be that the solution or the goal state has a depth of D, okay, and the goal state is at the most in the most right-hand corner of the search tree, okay, and other nodes with a depth of D have already been expanded. Okay, and the last node of D being expanded is the goal state. Okay, this will be the worst case scenario if we have a search tree that have a goal state with a depth of D. Okay, okay. We expand all the nodes in the search tree with a depth of D, but the last one is the goal state. Okay, okay. And as a result, we will see it will say a search tree like this, okay? Although the solution have a depth of D, okay, so you may expect that the depth D plus 1 layer is not being added to the search tree. But we are talking about the worst case scenario. And the worst case scenario of the breadth search is that the goal state with a depth of D is the last node being expanded for all the nodes with a depth of D. Okay? In this case, all the other nodes with a depth of D is being expanded, so you also see an extra layer of nodes with a depth of D plus 1. It makes sense, right? It makes sense, right, up to now. Because the breadth search is expanding the search tree in a layer by layer fashion. Okay? Where the depth D layer we get expanded, okay? We assume we take the worst case scenario in our thinking that if D is the worst case scenario, then the solution having a depth of D will be the last node being expanded among all the nodes with a depth of D. Okay, So all the nodes with a depth of D but not the goal state will get expanded, will get explored. Okay, so you can see a very long, a very long layer of nodes with a depth of D plus 1. Okay, it makes sense, right? The thing still clicks in, right? Okay, so let's do some math. Okay, so let's do some mathematics here. Okay, the first layer, okay, the first layer, of course, we have the root node, so the root node is 1. Okay, the second layer, the depth of 1, the number of nodes will be B. Okay, will be B. Okay, it makes sense, right? Because the root node, after expansion, the root node can have at most B, children node. Okay, so the depth of one node should have a number of B. Okay, 1 times B equals to B, right? Right? Okay. And if we consider depth of 2, each node in the depth 1 can have B nodes. Okay. So the number of nodes with a depth of 2 is B squared. Okay. You have B nodes with a depth of 1. So each depth 1 node can have B node as B number of nodes as a child node. So B times B equal to B squared for the depth of 2 nodes. Okay. And we can see a pattern here. So the number of nodes with a depth of D should be B powered by D. Okay. If we follow this pattern, then we know that the number of nodes with a depth of D should be B times D. B powered by D. Okay. Okay. All the things is just following the same rule, same pattern. So I will not repeat myself. Okay. And you also found that the number of nodes with D plus 1 should be B powered by D minus 1 because in the depth of D layer, in the layer of node with a depth of D, okay, one node is the goal state, so that node is not being expanded, but other nodes have been expanded. Okay, so the number of nodes with a depth of D expanded is B powered by D minus 1. And all these nodes can have it is already being expanded. So we times B with it. Okay. So as you can see here, the number of nodes with a depth of D plus 1 will be B times D powered by D minus 1. Okay. The things it's still unstable, right? Okay. All the things still logical, right? And we already figured out all the nodes in each layer. So we just add them up. Okay, so the next step is we just add them up. Okay, so we just add them up. And when we add them up, we found that the item with the biggest power is this one. B powered by D power times B. Okay, so the complexity, we just take the highest power item as the complexity. So the big O time complexity of the buffer search will be big O of B powered by D plus 1. Okay? Okay, and that's the reason why. Okay, and that's the reason why. Okay, so this is actually so that simple. Okay, we just analytically break it down one step by step. We can understand how this complexity factor being found. Okay. And for the space complexity, okay, for the space complexity, essentially, we just consider how many nodes we have in the search tree, then this is the end of the story. So it is also big O of B powered by D plus 1. Okay, you may ask, Professor, why this is the case? And the reason is simple. In buffer search, each time we explore all the depth, or all the node with a depth with an equal depth, okay, at once. Okay, we do it layer by layer. So every edge node, every terminal node in this search tree, we cannot guarantee whether they reach the solution yet. or they can never reach the solution. Okay. In depth first search, it is a different story. When we are using depth first search, okay, we explore a path up to the point we cannot explore further. Okay, so the moment we know that that path cannot get to the goal state, we can erase that from the memory because it doesn't serve our purpose. Okay, that path is a dead end. We don't need to save it in our search tree. Okay, so in the depth first search, we don't need to necessarily store all the nodes into the main memory. But in breadth first search, we need to do so because in breadth first search, we simply don't know whether the leaf node in the search tree is really a dead end. If it is not a dead end, then we cannot remove it from our search space. Okay, makes sense, right? So that is the reason why the space complexity of the breadth first search is the same as the time complexity. Okay, okay. So this is just a very rough explanation on the complexity. Okay, this is just to give you a general idea. Okay, I'm not here to make a very rigid proof. Okay, but you get the idea how these two complexity factor is originated from. Okay. And optimal mode, if the step cost is 1, then the breadth first search is optimal. Okay, okay, because it covered all the path with a depth of n before it proceeds to the path with a depth of n plus 1. Okay, so if the step cost is always 1, then breadth first search is optimal. Okay, but if the breadth first search is not 1, if the step cost is not 1, then it is not optimal. Okay, so some of you may think that the breadth first search seems to be optimal in some situations, and the reality is that it depends. It depends. It depends on what problem you are solving in the first place. Okay, so let's take the maze example. Let's take the maze video as the example. Okay. Maze. So in the maze, okay, each square in the maze can be considered as a state. Okay, so the cost transiting from one square to another square in the maze is always 1. Okay, so this maze is actually the example situation that the breadth first search happens to be optimal. Okay, because all each squares transiting to a neighboring square should always have the same cost. Okay, the cost should be 1. Okay, so in this scenario, where we run the breadth first search, you will find that the breadth first search is generating, okay, a optimal solution. Okay, and that's the reason why. Okay, from the survey, from observation, we believe that the breadth first search is giving us the optimal solution, and that's the reason why. In the maze, okay, each square going to the next square, the cost is uniform. Okay, so in this situation, the breadth first search is really optimal. So this is why you can see the breadth first search in this video is showing you an optimal path. But that is not guaranteed. It depends on the exact problem you are solving in the first place. Okay, okay, okay. I understand that it is better if we have a rule that is always being correct. Okay, but sometimes the world is not that simple. Okay, in this case, the breadth first search is optimal only when the step cost is always 1. If the step cost is not always 1, then it is not optimal. Okay, or if the step code is the same across all the steps, then the backward search will still be correct as well. Okay, okay. And the next algorithm that we want to talk about, and before we talk about the another algorithm, we will also need to discuss one of the issue about backward search. Okay, so we all already talk about the time and the space complexity of the backward search. If you take a look on the space complexity, you will see something like this: B powered by D plus 1. Okay, we see power for space complexity. Okay, that means that the amount of time, the amount of memory we need to taken, we need it to be for it to be taken to execute is extremely large. Okay, so as you can see in this diagram, we are showing the relationship of the number of or the depth of the search tree and the number of nodes in the search tree and the time taken and the memory taken. Okay, so here in this table, the first column is the depth of the search tree, and the second column is the node in the search tree, and the third column and the fourth column are the execution time and the memory taken. That is the RAM taken to execute the backward search. Okay, and also this is some tip for you. Okay, so in the future when you want to present a table to your audience, okay, you need to explain what is the meaning of each column and what's the meaning of the rows before you proceed. Okay, so here I just explained that the meaning of the column. Okay, and each row is representing the experiment on the performance of a backward search in a different in a particular configuration. Okay, so as you can see here in this overall table, we found that as the depth of the search tree decrease, the number of size of the node is increasing exponentially. We are just increasing from 2 to 16 for the depth, but the node already is increasing exponentially. So as the amount of memory we have to take to execute the search tree. Okay. So this table is actually verifying our findings here. Okay, the space complexity of the backward search is in exponential format, is in exponential scale. That means that the amount of time taken to execute the backward search the time and the space needed to execute a backward search will be extremely large. Okay. Okay. And so that is the reason why we have backward search and backward search. Okay. Okay. In some situations, backward search will perform quite well, but in some situations, backward search will perform better. Okay. So that's why we have two different strategies. Okay. We should pick the right strategy, algorithm to do the right job. Okay. And the next concept is called the uniform call search. Okay, when we are talking about the uniform call search, okay, we are actually doing some modifications on the backward search. Okay, essentially in backward search, we are prioritizing nodes that have a lower depth. Okay, they shadow. Okay, so now can we create an algorithm that prioritize paths that have a lower cost? And in fact, yes. Okay, we can totally create a algorithm that prioritize not having a lower path cost. So we can find an optimal solution for this algorithm. If we try to explore the nodes with a lower path cost each time, then we can always find the lowest solution that is optimal. Okay. Okay. And that is called uniform call search. Okay. And one thing you must remember is that for uniform call search, it only works if the step cost is not is a positive number. Okay, it only works when the step cost is positive. Okay, if the step cost is negative, the uniform cost search doesn't work. Okay, and the reason why uniform cost search is optimal is too involved that I will not discuss in this lecture. Okay, you can just take it for granted. Okay, the uniform cost search will always find a optimal solution. That is the solution with the lowest path cost if all the step cost is positive number. Okay, you only need to remember one thing. The uniform cost search can only give you optimal solution only when all the step costs are positive number. Okay, so any questions? So when we want to prioritize the expansion of the path of the, if we want to expand, if we want to prioritize the expansion of the nodes that have a lower path cost, one thing we need to take into consideration for selecting node for exploration, for expansion is the path cost of the node itself. Okay, if we want to prioritize node that has a lower path cost, we need to have a data structure that can do that prioritization in the beginning. Okay, so in order to discuss this data structure, I need to ask every one of you a question. Have you learned a tree called heap in data structure course? I repeat, have you learned a data structure that is a tree called heap in your data structure course? And in heap, you learn one thing, right? The root node is always the lowest value, right? Okay, the root node of the heap is always the lowest value or highest value, right? Depending on how you implement it, right? Right? And what if we create a heap, okay? That the data structure that is storing an element with two items. That is the key and the data value. The items are stored in the heap with the key value. Okay, the ordering of the element stored in the heap are arranged with the key of the item. Okay, and each time we are receiving an item from the queue, from the heap, we are retrieving it based on its key. Okay, imagine this: we have a heap, but now instead of storing a single number as data point in the heap, we store a key value pair in the heap. Okay, and the elements are stored in the heap based the positioning of the key value pair are stored in the heap based on the value of the key. The key value pair having a key with a lowest value will always be in the root. It will always be in the root node. Okay? 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 So if you implement a heap in this manner, then this data structure we can give a new name to it. It is called a priority queue. Okay? It is called a priority queue. So when you take the data structure course, have you heard of a thing called priority queue? Anyone? Anyone? So you learn heap, right? But you don't know it's priority queue. Okay. Okay. So let's imagine this. Imagine this. You can store whatever things in the heap, right? Where? Just as long as you have a mean to determine which value is bigger than the other, which element is bigger than the other element, then you can have a heap, right? Imagine this. I am storing a key and a value pair into the heap. And I'm arranging the key value pairs with the key. The key value pair with the lowest key value would be in the root node of the heap. Okay? So now what you have just done is you created a priority queue. Okay, a priority queue essentially works by the fact that when you insert a item into that queue, you also include its priority. And the element, if we retrieve the tool, when you retrieve the element with the highest priority or the lowest factor, okay, something like this, will get selected. Okay, so that is the meaning of priority queue. Okay, and that is why before I talk about priority queue, I ask you whether you know heap. Because one of the easiest way of implementing a priority queue is using heap. Okay, okay, and in fact, okay, the one of the main reasons why you want to learn heap in the first place is the heap is a very beautiful way of implementing a priority queue. Okay, and that's the reason why you learn heap in the data structure course. Okay, but in this course, so as you can see here, we replaced the fringe with the priority queue. Okay, with the priority queue. Okay, okay. And when we add the element, when we add a node into the priority queue, we also include the path cost of that node. And the path cost is used as the priority. That is, the node with the lowest path cost will get selected for processing by the priority queue itself. Okay, so at the end of the day, we are still following the general tree search algorithm, but this time we are using priority queue to do the priority selection for us. Okay, and you can see that I am using a data structure built into Python, and you see the name actually already gives you some hint on how it's implemented. It is called heapkill. Okay, heapkill. Okay, so this is the reason why I asked you whether you learn heap first. Because one of the most common way of implementing a queue is implementing a priority queue is using a heap. Okay. So as you can see here in the extra notes, okay, I actually also included a example of implementing priority queue with the heapkill library. Okay, and this is a sample code that you can refer to. Okay, so in the future, if you are working with other projects that require you to use a heap or priority queue, you can also use it as well. Okay, you can use this library to easily implement a priority queue. Okay, I believe that in some situation you will need to use it. Okay, so you can take a note on it. This is already included in the extra data structure, basic data structure notes. Okay, so you can refer to it. Okay. And here are some examples. And here are some explanation of how this library works. Okay. The first argument is the list. Okay. Before you we work with a priority queue, you need to first create a list. Okay, and the list will be the data structure that store the data, that store the priority queue. Okay, but instead of interacting with the list directly, you use the heapkill function to interact with the list. Okay, so essentially we hijacked the queue. We hijacked the list. We create an empty list, and then we use the heapkill heap push and heapkill heap pop to hijack the list. Now you do not address the list directly. You address the element in the list using these two functions. Okay, and as you can see in these two functions, it takes the list we just created as the first argument. And this list is storing all the information about this priority queue. Okay, and then right after the push, you see a tuple. Okay, you see a tuple. Okay, in the first value of the tuple is the priority, and the second value of the tuple is element. Okay, so the element. So the priority is done with a lower value means a higher priority. Okay. So if you want to prioritize smaller values, okay, then this will just work out of the box. Okay, it prioritize lower priority over higher priority. Okay, lower priority value means higher priority. Okay, that is if you fill one here, then the one will have the higher priority over 5. Okay, okay. The smaller the value, the higher the priority is. Okay, is in reverse. Okay, but it is not that if you want to make this structure with a high value means higher priority, you just put a negative value to it. Okay, okay. You just put a negative value to it. Okay, then you can convert into a system that high value means higher priority. Okay, okay. But here, lower value means higher priority. Okay, so this is how it essentially works. Okay, and as a result, this is the reason why initially we create a list called PQ, and then each time we interact with PQ, we use the heap Q dot heap push and heap Q dot heap push to interact with it. Okay, and when we add element into the queue, the first value in the tuple is the path call, the second value is the node. Because the first value is the priority, and the second value is the actual element that is included into the queue. Okay? Okay. So any questions? So if you do not have any question, then I think this is now a good time for us to start today's lecture. Okay. I will see you in in the next lecture. Okay. I will pause the recording. Okay.